Hello. Okay. Yeah, no, yeah, the problem is this is a workshop. So, and the code, I'm not sure how I will be able to take all of the students together. So we'll take breaks in between and let them catch up after each of the exercise. And I'm also not sure how much time it will take for each exercise. So the way I want to do it is I'll cover basic concept and one example, code example, using explaining that concept. So the code is all written. So I'll send the code at the after I made the explanation for the concept. That way, the codes are slightly longer. So earlier I used to let everyone type by hand, but those codes were like 4 or 5 lines. But now they are slightly longer and better to just copy and paste it. Yeah, yeah, we can. That's the problem. I'm not sure how long this will go. If it is only copy pasting, if we might be over earlier as well. Yeah. So, how many? Sorry, how many registrations have we got? 48. Yeah. And so, what is the background? So, this IEEE chapter, you have students uh, involved with astronomy or only like technical background? Okay. Yeah. Yeah. Hmm. Yeah. Yeah. So the codes, obviously, yeah. So the only problem is that although the concepts are very basic in astronomy, but this session would be more of a class on those basic concepts only. So, like coordinate system, RADEC, altitude azimuth. So we'll play around with that only. In fact, it's only one library that I will be covering. And in fact, my background being from outreach, I've only like uh, I only cover only from that point of view. So there are obviously many specialized library for different research. Well, in fact, in the initial 2 3 slides of my talk are only explaining that only, like AstroPy, and there's a whole list of libraries specialized for each field of research. Yeah. Yeah. So we'll start at 6 o'clock, right? Yeah. 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 The other thing is, if people are joining late, then there might be a problem. So initially, maybe we'll take 5 minutes or a few minutes to make sure that everyone is on the same page. They have a working terminal or a notebook open. Okay, so right now around 14 people have joined. So are all of you like ready to program as well, or hello?
Good evening, Alok,
Yeah, good evening.
and this is Chalam from Hyderabad.
Yeah,
Yes, I'm into astronomy,
yeah.
and I'm keen, and I have uh, very fundamental knowledge about it.
Yeah.
I'm a to be called as a novice, not an expert on Python, but
Okay.
I'm in the course of learning it. And we, along with one of my friend, I did write some programs for Python, and we are
Mhm.
continuing. That is my background.
Okay. So no, right now, even if you haven't, my question right now is I would want everyone who is coding with me, at least today. If you're not coding, that's also fine. But if you are trying to catch up and run the code that I am running, you need to have those libraries installed. I think you would have mailed the
Yes,
link.
I have installed all the libraries what you have recommended.
Yeah. So any issues? Did anyone
No,
have any issues with?
I didn't have any issues. Everything is smooth.
Okay. Yeah. Anyone else? So the basic thing is if you are using Anaconda or even if you are not using Anaconda, two, three things that would be needed. The most important thing is the Skyfield library. So you can do that using pip install Skyfield. But if you are not even comfortable with installing a package, then that might take some time in handholding.
Yeah,
So
I did install, but
yeah.
I did not install Anaconda.
Yeah. So those who are not using Anaconda, I'll right now I have a Jupyter notebook setup, and
I have a Jupyter notebook.
yeah, yeah, okay. So the way we'll do is I'll copy and paste the code after each exercise
Yeah,
in the chat box here in only, and you
yeah.
can paste it in your notebook. If you don't have a Anaconda or Jupyter notebook or anything set up, still it can work if you save it as a file and run it or paste it in Python terminal. But
Oh,
that might be easier way would be a Jupyter because you can edit and run
yes,
it there.
yes, we can. Jupyter I have
Yeah.
browser based.
Google Colab, what would that mean? Uh, yeah, so what we can open Jupyter on that or how it
Yes,
is?
actually, Alokji, Namaskar. This is Amritanshu. And
Ah,
actually, right now, this is the collab is the Python implementation provided by Google in one of the applications. So I
okay.
just wanted to know that whether under the scope of the lecture, will this collaboratory will work or not?
Okay, we can try that right now. I have an browser tab open with Jupyter Notebook and I was about to share that. So we can try if that collab is working
Okay,
and
sure.
I can run
So
code.
what I will do is on the sideline after lecture is over, I will share my feedback on collab also with you personally.
Okay, okay.
Thank you.
So right now, maybe we can try. What's your name? Arjun. Hello. So can you try it right now? We have like 5-10 minutes. Otherwise, I can share the screen. That notebook, my notebook would be visible to everyone anyways. But what he's referring to, if we can do that, okay. But then whose environment will be used? We'll need to install our dependencies in that. Okay. Okay.
It is cloud-based Jupyter, if I'm not wrong.
Yeah,
Cloud-based, yeah.
okay, but then still, how would you open it in Meet? Can one try right now?
Yes, see, I have just. Yeah, if you want, we can share the screen. May I for a time being, a second or so?
Uh, I should share my screen.
Yeah, no, no. If you want me to share the screen, then if you want, I can share.
Yeah, so
But
it
I
would
do
be
not know.
sharing the screen or a collab. So the thing
No,
to be projected would
okay,
be the
okay,
collab screen.
okay. So what I am going to do, I am going to put the link here, Google Collaboratory.
Okay, okay. Collab.research. Upload. Let me see if I can upload one right now. Uh, I think I've opened it. My code is also running there. The thing is, I'm not able to share or cast it. Let me just wait. What I'll do is I'll share my screen now.
I think if everybody is on the same, like Jupyter or something, it will become easy for execution.
Is it shared? Okay, so this I have my own notebook set up here, and I'll keep on pasting the examples and my slides. But anyways, I'll need to keep on jumping from the slides to this, right? Okay, yeah, there is an error now. A module not found, but initially it ran. I'm not sure why. No module, yeah. That's the thing. Okay, fine. No, not on this collab. Initially it was showing the
No,
result. Yeah, but that was
in the collaboratory, you may have to put it with the help of PyDrive exclusively. So Alokji, I would not say that you do it now. You may
yeah,
do
yeah.
it later after installing the things in PyDrive.
Okay. Anyways, yeah, because I would need to keep on changing tabs here. So, okay. Yeah, so I'll close this. But yeah, I don't see an option to cast it in the Google Meet. So people can open this notebook on their browser tab, but again, they would have also have to switch in between. But yeah, anyways, they would have to do it for their own programming as well. Yeah. So between the Google Meet window and this Jupyter window. Yeah, the results are cached, so I can see the results, previous result. I think once I uploaded it, the previous outputs are being printed here. Okay. So what I'll do is I'll maybe try to, if I think it's better to have the doubts in between, because when we are covering the concepts, there's no point in holding that doubt till the end, because the main purpose of the example we'll be covering is to implement that concept. So I think we can feel free to ask the doubts. You can all feel free to ask any conceptual doubt that you may have.
You can share because those for the benefit of the people who came early, you can share so that everybody can be ready. We can
Uh,
save the time.
what did you say?
The the code which you said you will be sharing
No,
it.
no, I'll keep on sharing it. So I'll
Share.
keep on.
Oh,
I can share it right now, but it would be very long and confusing
oh,
anyways. I'll cover the concept and then share it with everyone, so they can copy
okay.
and paste it
Yes.
instantly.
Okay. You'll be putting it in the chat window.
Yeah,
Then
yeah, chat window. So please keep monitoring that. I'll
okay.
anyways tell you when I'm pasting. So once I'm done with the explanation of one topic,
Yeah,
then
that
we'll
would be nice.
jump. Yeah. So that is how I've structured it. I'll cover what the example is, what the concept is about. Have a bit of discussion about it. Then you can ask any doubts. And okay. The concepts are very basic. If but yeah, if you're not done astronomy courses like astronomy 101 in colleges, then this would be a very useful thing. In fact, the whole session is only for that. There is no, as I said, there is no specialized research tool that we'll be focusing on. It would be general purpose astronomy calculations with Python. Yeah, I think I remember I had one, not a workshop, a lecture with IEEE Gwalior. This was like, I think more than 7 years back now. Last I was giving a lecture in an IEEE chapter was in 2016. in MIT's Gwalior. So I had many students contacted me. Now I think it's after so many years again. Yeah, yeah. Even the student who initiated or took initiative in that Gwalior one was one of our students. So one of our students in Harvard. So he was in college and then he was interested in doing outreach in terms of astronomy. So we took a couple of telescopes. In the night time, we again showed the sky, and daytime I took a lecture on basic astronomy. But this was not coding. In fact, the coding workshops I have taken were in Nehru Planetarium only. So Ratnashri ma'am, if you guys are aware, she was very active. So she had like annual summer camps for coding for college students. So I took generally one of the sessions on ephemeris, the topic that I'll be covering, and she invited like many researchers from different topics, and one day per topic, sort of a session, whole for a whole month or two. She used to organize this summer code camp sort of a Yeah, yeah. In fact, there are many, many outreach groups that I am in touch with now. And yeah, as you said, I don't have many contacts from Kolkata. I have one Facebook friend I remember. I think he's a senior person, Devi Prasad Duari. I think he retired from Planetarium or something. Maybe you would have heard it. Yeah, so because of my apps and outreach, whoever is in touch with me. But yeah, I have seen the many enthusiasts have added me on Facebook, but I haven't seen Skywatch watching groups or parties being organized there. Most of them are in Maharashtra and south of India, Gujarat, even Rajasthan and Delhi, obviously. So all these are we are in central India. So many of the states are active and having such sort of amateur groups. I saw your post, so at least you are doing a good job in that front. But yeah, the obviously one thing is Kolkata is like a big city, so you're not it won't the sky won't be that good. But even without yeah, so same is with Delhi and Mumbai, but still there are things that can be done. So
You,
maybe
Alok, you have anybody from Hyderabad?
Hyderabad, Priya Hassan ma'am, I think she's a professor in Maulana Azad University. So
Yes,
she's
yes,
doing
Priya
a lot
Hassan.
of work. But yeah, that those in practical terms also, I think there are a couple of groups. More are in Bangalore. So I know, I think Triple A or something, Amateur Astronomers Association in Bangalore is there. I'm trying to remember an amateur group in Hyderabad. I'll see because most of them I see a lot of these events on my feed. So I'll try to see if I get some contact from Hyderabad. I'll be
Because
back
it
in
is
1 week. Yeah,
unusual. We are
yeah,
getting interested after we are 60.
yeah. Okay, I'll be back in 1 minute. Let me get some water. open, or you can, if you are comfortable, you can just paste that code in a file or a Python terminal itself. The prerequisite for that is a Skyfield library and a couple of more libraries. I think the instructions would have been mailed to you once after you had registered. So let me see if I can find the prerequisites beforehand. Wait. I'll show the prerequisites here. So you can, okay, I'm sharing, if you can see my slides here. Yeah. Now, yeah, these are the slides. These are the libraries that you should install. So first and foremost, you should have a obviously working install of Python ready, Jupyter notebook. Then, if you have a working installation of Anaconda, on the first 2-3 parts would already be installed. Matplotlib and Pandas, all these things are needed. But the most important library that we'll be using today is Skyfield. So if you haven't installed already, you should go and install it right now. You can install it using pip install Skyfield from the command line, and make sure that once you load the Jupyter notebook that you'll be using, you can import the Skyfield the command. I'll show that. Okay, once we get to that. These are the prerequisites, and it's fine if you don't want to follow it right now. I'll share all the codes together in a notebook later on, so you can follow all these examples one by one after the talk is done. Okay. So yeah. So that's the first thing, hello world. So those who are following, I have also my Jupyter notebook open here. You can also try out hello world and obviously see whether the Python or Jupyter notebook is working or not. Then let me see. Then there is one more code that you should try and run. So if you have already installed the Skyfield library, try and run this code. Okay, just importing one of the functions from the Skyfield library. If it's giving a module not found error like it is showing here, see, if this is the sort of error you are getting, then you'll have to install that library. Okay, so I'm assuming in the meantime, I'll start with my slides. In the meantime, you can try and get this working if you are following the code. Okay, so yeah, this is also done. So, okay, let us start now. So why this workshop, astronomy with Python? Although the poster says astronomy and Python, what basically we are doing is trying to do some astronomy using the Python language. So as you can see, and you would have heard of this also, that in 1960s, when NASA or the US landed first time on the moon, it was achieved with a computing power that was less than a calculator. The code is also old now. So when it reads here that the computing power less than a cell phone, this is referring to the Nokia era cell phone, not the cell phone that we have now. The cell phones that we are now having in our pockets, Android or any smartphone, they are like mini supercomputers. The computing power that they have is a lot. Now, so after the NASA missions to the moon and the space missions, there was a lot of interest in astronomy. So before that, obviously, before the advent of computers, all the computation meant in astronomy was very tedious. And we'll see how it was being carried forward. But after the advent of computer, it was something that every person can do. Today, all of us will be doing the same calculation. Obviously, not the same that were used for taking the man to the moon, but the basics of that will be covered. Okay, so some of the thing. Okay, let me clarify what we'll be covering today and what not. So AstroPy is one of the most important libraries being used in research in astronomy nowadays, and it is you will be able to do a lot of things with it. So here is a list of fields in astronomy. So basically, I've taken this list from the website of ASI, Astronomical Society of India. These are the different themes in which I think they were expecting papers. So the sun and the solar system, stars, ISM, galaxies, extragalactic astronomy, relativity and cosmology, and instrumentation. I think if you are most of you are engineers, then you would be interested in the final one, and that the instrumentation and techniques involve data handling with CCDs, the whatever optical or radio astronomy. If you do, then the data that you get, how to analyze it, how to reduce it, and how to use it in research purpose. So all these things would come, I think, in this one. So there are specialized library for each and every one of these research topics. So we are not going to cover that. So the main aim of today's workshop is to get you started with the basics of astronomy, and obviously basics of astronomy in Python. So the library again, yeah. So this is a list of some of the libraries that are being used in astronomy research. As you can see, this is also not a comprehensive list. Obviously, there are many more libraries. So depending on if you get into astronomy research, you will need to use one of the others. So yeah, this is the library we'll be using today. Yeah, so the name is Skyfield. As I said, I hope you all have it installed, and we'll be covering only basic astronomy. By basic, we mean positional astronomy. Okay, so all the topics of research I mentioned earlier obviously are very much advanced than this, but still, this is something that all of the astronomy community, in fact, everyone should know what I'll be covering today. So as I said, before the advent of computers, how was astronomy done? So this is something called an ephemeris. In the right, I think I've taken this from Wikipedia, and it's in Latin or Greek, some olden script. So basically, Latin ephemeris means diary, or simply a journal or list of data points. So this is how astronomy was being done. I think many of people are still using this sort of data sheets if they're not comfortable with computers. So what ephemeris is basically is just a table showing the maybe the positions of planets or stars for every day or for any given specific periods of time. So before, obviously, computers were there, they had to be compiled by hand, and for that, models of planetary motion and all were in place. But now, since we have computers, we can do that with a lot more precision, and obviously we don't need to print thousands and thousands of pages for such data. Okay, so all this that was being used hundreds of years ago, now we can just replace with few lines of Python code. You will see. Okay, so yeah, this is ephemeris. So one of the most prominent and most accurate ephemeris being used nowadays is from NASA, and I'll try to open it. Yeah. I guess you can see this. Yeah. So why is this such precision needed? So initially, if you look at the ancient astronomy, the ephemeris were only used to see for sighting of the planet. So it didn't matter if the position of the planets, the sun and the moon were off by a fraction of a degree. Obviously, it mattered in timekeeping and calendars. That correction was needed. But if you thought of planets, it mattered only in astrological purposes, not any scientific research purposes, because the only method of seeing before that was through the eye, and obviously eye will not be able to resolve such details. Now, when the telescope was invented in 1600s, you could see with a lot more accuracy. Still, it wasn't even 0.01 degrees of accuracy would mean a lot of deviation in terms of absolute position of the planets. Now, after the World War II, when there was Cold War and basically the race for space was there between Russia and USA. The first race was to go to the space. Yuri Gagarin was the first man, and Russia won that. Then the NASA spent a lot of money and effort to get first to the moon. Now, to get to the moon, you are basically launching a rocket and you're trying to land it there. So it's a very tricky thing. You have to have the accuracy of positions of the moon within meters. It's not enough to send because lives of people depended on that. So you can't just estimate the position of the moon and correct it using the sight of the astronomer. So that's why all these missions, even now that NASA, even ISRO has now joined and sent its mission to Mars in terms of Mangalyaan. Now, so for launching such sort of missions, the accuracy needed is in meters. So if you want to land a rover, you need to precisely know where it will land, and obviously corrections are made, but still your model should be accurate till meters. So the site I have opened now is called Horizons. So it has different ways to get and different APIs to get positions of different planets to a very high degree of accuracy. Now, okay, so this is a Horizon system, and let's see if so yeah, so there are different models inside this portal as well. You don't need to go into all of that. I covered this because the first example, in fact, all the code that we will run in Skyfield, we will be using one of the ephemeris files from this system. Okay, before we start, a mention of Positional Astronomy Center in Kolkata. So whatever we are doing, it's a coincidence that the government organization in India that is mandated to do all this is in Kolkata only, and it's called Positional Astronomy Center. Maybe some of you would have heard of it. And this Positional Astronomy Center, there is something called Rashtriya Panchang, or Indian National Calendar. Not many of you would know this, but the official calendar of India is New Year is supposed to happen on vernal equinox, or 21st of March. So it's a different topic in itself. But the government mandated in 1957 to keep all the ephemeris updated. So this Positional Astronomy Center in Kolkata, let me just open it here. So I think my screen is still shared. I can open the website. You can see, and you can open on your own web page also if you want. So it is having an annual publication. As you can see, it publishes Indian astronomical ephemeris every year, and it publishes Rashtriya Panchang in different languages. And you'll see that its task is solely to give out ephemeris tables for different events like rise and set timing of sun and moon and different astronomical phenomena, and tables for stars and other planets. Okay, so this was also mentioned. You can also download all these and take a look at your own. So what we will be doing is the same task that they are doing. Now with the power of computers and Python, we will be able to do all of that with the same accuracy. Okay. So yeah, Indian Astronomical Ephemeris is published annually and by the PSC Kolkata. So here is a screenshot from one of their ephemeris. You can see this is, I think, for this month only. So this is for the sun, and what it is showing is for each day of January, the position, geometric longitude, latitude, apparent longitude aberration, and many technical terms. So the first part, before each example, we'll try to cover what these terms are. We won't go into all of the examples, but after this workshop, we'll have a basic idea of what different data points are there in an ephemeris. One of the files that we'll be using in all the code is de421.bsp. So as I showed the NASA website of Horizon, there are different models with different accuracies. So I think most of the examples that we will be using will use a file called de421.bsp. So it is approximate model. I think around 5 to 10 MB of size of file will be downloaded once you run the code. So you don't have to download it yourself. The code will do that for you. It will do it in background. So there are more accurate files that can be used for more accurate positions of planets, but this is the one that we'll be using. Okay, so let's start. As I said in that notepad, you should have installed Jupyter, Skyfield. NumPy will be installed alongside that. You don't have to install it separately. Matplotlib, In the end, if we have time, there are a couple of examples that will involve matplotlib. The initial 5 or 6 examples won't have that. So I think pandas is also needed in the last example. So those are a bit advanced. We might not be able to make it up to that, but if we have time, we can cover that. Okay. Okay, so this is the first example. I'll just paste this code in the chat code. Okay, so and we'll go through what each of the line is doing. So this is just to get you started. This example is where is Mars? I'm pasting this in chat box. Can you everyone see? I've pasted it in chat box. You can copy this and paste it in your Jupyter notebook. I'll also do that. So in the screen, you'll be able to. Sorry. Yeah. So I have an empty sheet here. What I'll do is I'll paste here. This is how it should look for you as well. Okay. So I've pasted here. I hope everyone has pasted, and you can just press run here. Okay. So everyone, whoever is trying to run the code with me, is everyone on the same page? Have they pasted this and did it run successfully? Anyone is having an issue? So let me know. So this is the first example, the easiest one.
We got the same answers.
Hello.
We got the same answer.
Yeah. So so everyone should be able to run this if they are having an issue. Yeah. So we are running it at the same time. So yeah, so the name of this example is where is Mars? Okay. Now I should write this here as well. Where is Mars? So what we are doing is what we are doing here is the first line is we are just importing a function called load. Okay, just keep it. Don't bother about the technical terms for now. Anyways, I'll give you an advice. So if you have a good understanding of coding and programming, so don't bother about learning syntax or functions. I think many interviews and exams might give weightage to that, but a good programmer or good programmer does not need to memorize everything. Google is your best friend. What you do need to understand is how to make a code and how it basically works. So that understanding is more important. So I'll just go through line by line. So first of all, we are just importing. Most of the people would have had a problem here. So if everyone is having properly able to run the code, then I think everyone has this installed. So then there should be no issues in future in further examples also. So yeah, so first line after that, we use the load function to load a time scale, and we use t equal to ts dot now. So you can now play around. The reason why we have chosen notebook is we could have done this on terminal. So those who are not using Jupyter, they can also play around in their Python terminal. For example, the t variable is now storing the t value. Now I'll type t in the next and run. So you can see it is basically a time. The time basically it showed is the time stored at the time of that running. So if you open it after 1 hour also, it will show the same time unless you run this again. So at the instant this code was run, that time is stored in t. Okay. Now, as I mentioned, DE421. So this load function is again being used to load this D421.bsp. Now, if you have time, you can look through your file system. You will see that this D421 file, I think, is downloaded in your, depending on where you have opened or run the Python or the Jupyter notebook. Let me see. Mine is a Windows system, so it is in my home directory. So you can also search for it. I think the size of it is D421. is 16 MB, so not very light, but 16 MB of file. So there is one more called DE441, which is like 3 GB, and I have used that to. I'll come to that in another example. So there are different files that can be loaded depending on the use case. So just to get a general idea of the Mars position, this is enough. If you are ISRO and you want to send something to Mars, obviously this file is not accurate enough. So you need even a bigger file for that. Okay. Now what we are doing next, we are just loading two variables or two planets in variable Earth and Mars. Planets Earth. So this is sort of a dictionary lookup from the planets. You can consider it as a database. So will not go into intricacies of Python much, but just from this database, you extract Earth and Mars, and you assign it to here. You can try out each of the variables. So I'll type Earth here and run. So you can see what is it. It's very insightful. You can see that it's basically vector sum of two vectors. Solar system barycenter, Earth barycenter, and Earth barycenter to 399 Earth. So basically, it's an internal representation. It might seem very complicated because it is. So basically, it's an internal representation of how the calculations will take place. So all you need to know is that Earth is now stored in, and the internal representation you can find at this bottom. Now, again, there is one more technical term. We can ignore it right now. Astrometric. Okay. So what we'll do, why we loaded Earth and Mars. What we need to know is where the Mars is when viewed from Earth. Okay, so we'll do Earth dot add t. So it also obviously very important when you are looking at it. Depending on the time, the position will change from Earth. Observe Mars at time t. So Earth dot add t dot observe Mars. So this library is very functional in nature. So we'll find out later also. You can chain along different functions to play with the data. So this is the viewing point. At this time, the point of observation is Mars. So this position coordinate is astrometric. Okay. So this astrometric, I can just paste here and run. Yeah, I think there is a doubt from Pranshu. Yeah, go ahead, Pranshu. What's the doubt?
So how can we change the variable t? Like if we want to see Mars in a different date for a different date, then how can we vary that variable?
Yeah, I already have that in next example. I'll just copy it here. You can paste. So T1. Okay, so instead of ts.now, what you can do is ts.utc 2023. So year, month, date, hour. I think you can do minutes as well. 20, 30, 30. Let me see if I have the correct syntax here. Yeah, T1. Okay, see, so this is how you can do it for other times as well. ts.now is just a shortcut to get the current time. You can obviously change or get any time you want. UTC is GMT, so this is not IST. This time is in GMT. Okay, so everyone is following this right now. Any doubts till now? Okay, so I'll move on. Okay, so now the three terms at the bottom here are RA, DEC, distance. So the output that we get in this astrometric, okay, let me put astrometric. What is astrometric? So even I don't know the data type. Okay, we can just find out. So astrometric is ICRS position and velocity at date T, center 399, target 499. So these are not important. These are, I think, ID numbers for the objects. But what is important is ICRS. So I'll come to ICRS later. So, okay, so this first example is done. So I think most of you would know nothing about RA-DEC. So to make sense of what we are running and what is the output, we'll now jump to the first part of our lesson. Okay, so now this is done. This whoever is following the code was able to run this. Yeah, as you can see, it's also written here. The D421 covers 1900 to 2050. What that means is in this date range, the positions are accurate. And after that, obviously, they'll diverge. If you want to find the positions for historical purposes or for date too far in future, you have to use a larger, bigger JPL ephemeris file. Okay. So we now jump to ALTAS. Okay, what is ALTAS? It's short for altitude and azimuth. Okay, what I'll ask everyone to do is, if you have an Android phone, I think that is in the next. Yeah, if you have an Android phone, just do one thing: download this app, search for Altaz in Android, and install it. Okay, it will come in handy to understand the concept. I'm waiting for a few seconds. Everyone, if they want, they can install it right now. I'll try to show my emulator screen and what you'll be able to see. Yeah, here it is. Okay, so everyone is able to install and see. Yeah, so this is basically a 3D compass. Okay, just move the phone around, and there is one more way to change it. So I think on the top right, yeah, if you can change, if there are two modes, fixed, you can change this fixed to check or uncheck. So I'm problem is I won't be able to move this emulator. Let me see if there is a way. I think there was a way to change the orientation of the emulator as well. Yeah, I got it. So location, orientation. Anyways, yeah, it's better you try it on your phone. So no point in for me in changing the orientation of the emulator. So you move around, you'll see the this line is also moving. So what basically is this line showing? So ALTAS is basically short for altitude and azimuth. Okay, and these are called local coordinate system. So when you are basically right now standing on the surface of the earth, you are looking at the sky as an hemisphere, so you only see half the sky. So you can imagine the whole of the universe, we see it as projected on a ball, basically a sphere, and the earth is blocking half of it, and the this half of it, we basically are seeing it as a dome or a hemisphere. Now, this coordinate system is basically a spherical coordinate system. So if you are good in maths, you would know that there are in spherical coordinate system, there are three things. One is r, the radius. The other two are angles that are sufficient to give the position of any object on the surface of the sphere. And r is basically variable. But in this case, r is infinity. So for us, everything is on like very far away. R, we are not bothered with r. The two things that we measure are altitude and azimuth. So the azimuth is basically the direction of any object, right? And the other important thing is altitude. So just think of any object in the sky. Just if you go outside right now, you'll find Jupiter, Saturn, and I think Saturn might be set, but Mars would be very high up in the sky. And you'll be, especially in Kolkata, I think sun has set in Kolkata quite earlier, quite a bit earlier. So you can see some stars are higher in altitude. Altitude basically means the angle the object makes from the horizon, right? So just to be technically clear, altitude is the angle the object is making from the horizon, and the azimuth is you drop that perpendicular line onto the horizon, and the measure clockwise the angle direction from north direction. So 0 degree north, 90 degrees east, south is 180 degree, and west is 270 degree. So basically anything on the horizon will have an altitude of 0, and everything basically on this sky we can give an ALTAS coordinate. Now this is called a local coordinate system. Why is that? So let's just take an example. I just told you that Kolkata will have a sunset earlier, right? Right now I'm in Bhopal. I think some of you have joined from Mumbai, and many of you have joined from Kolkata. You would know that the sun would set early in Kolkata than it would for the other cities. Now, if I were to take the coordinate altitude and azimuth of the sun, let's say in Kolkata, now the sun has already set in Kolkata. That means the altitude is less than 0. And if at the same time we are right now on the call, and I do try to do that same thing here, I think it is set here as well, but maybe let's say in Gujarat it is about to set. So you'll see that the object will have different coordinates in each and every plane. That's why it is called local coordinate system. Okay, so this coordinate system is very useful because it's precisely giving you the position of an object, but the problem is it is local. As you saw the first example we ran of Mars, it all of the users would have gotten the same thing. The first thing is because it's not in Altair. The other thing is with the time also was taken in UTC. So if we had participants from different countries, they would have different time zones. But since the time was in UTC output and the coordinate was RADEC, that problem was solved. So the most important basic coordinate system in Altair. So to get a hang of it, what you can do is now you have it on your phone. So the way to use it, okay, I'll show it on mobile also. So this is the phone. So along this vector, along the surface, you take a line. So this point that it is pointing to along the surface is the one reading you will get. So and this is a very useful tool. So if you have learned trigonometry, you know that you can basically use trigonometry to find heights of buildings and all that. So this is basically very useful in that also. You can just line up the phone surface to any building and measure the altitude of that. So that way it will give you the altitude of any object, terrestrial or celestial. Okay, and the azimuth also. Azimuth is the direction. Okay, so this play around with this app, you'll get an idea. Okay, next is now as I told, this was local coordinate system, right? It changed with every city. For Kolkata, it is different. Even from Kolkata, if you move around 10 kilometers, it will be slightly different. Even 1 meter movement it's enough to change the value. Obviously, it would be the change will be less. So what is the solution for that? So the solution for that is equatorial coordinate system. Okay. So that is what the output was for the our first example, the Mars example, RA and DEC. This is the coordinate system used for celestial objects, and this does not change with location. So if you want, if in astronomy you see the position of any object and change of position or whatever, the coordinate system mostly used is RADEC. Then there are different coordinate system, galactical coordinate system, where the origin and the axes are aligned with the Milky Way galaxy, and ecliptic, and a couple of more. So there are obviously various coordinate systems used, but the primary one that you need to know is RADEC, and it's called equatorial coordinate system. Right? If you look at the image right now, the understand sky coordinates image, you will see that it's very similar image. If in geography you would have seen or learned about latitude and longitude, this looks very much like that. So yeah, so this is a map of the Earth, and the horizontal lines are the lines of latitude, and the vertical lines are the lines of longitude, right? So it is something similar. Similarly, the second image now that you see is the sky map. So like the globe, the spherical Earth is being projected on a paper here, the whole of the sky is mapped in this image. You can see it mapped just like the surface of the Earth. And like latitude and longitudes, the lines are drawn on top. So again, here same corresponding to latitudes, we have the declination lines, and corresponding to longitude, we have right ascension line. Okay, yeah, this is the thing being shown here. Now, the equator is an important thing on the surface of the Earth. Equator is 0 degree latitude. Corresponding to that, there is what is called celestial equator. So just imagine all these grids on the surface of the Earth. Obviously, these are virtual, but expand them and expand them to the sky. So the same lines you can extend infinitely and project them on the sky. The corresponding equator will become celestial equator, and the lines of longitude will become lines of right ascension. Yeah, but the thing is, we need a GMT, right? There needs to be a starting point So the convention on the Earth is to follow Greenwich Mean Time. So longitude from London is considered as the starting point. Similarly, for the sky, that point is considered as vernal equinox, right? So I think I'll cover this topic later, vernal equinox. So, but this is where the sun will be in the March equinox. Okay, so that point we consider it as the starting point of longitudes, or rather right ascension. So this is the standard. Now see what happens. Now you have given coordinates in the celestial sphere in the sky. Now if we consider the position of the sunset that we were considering, at the time I was talking about it, Kolkata, Gujarat, Mumbai, Bhopal, all would have given different altas. But if I was talking about RA deck, the position in RA deck would have been the same for from every location. And we can even try that in one of the examples. We can change the code and see. Okay. Okay, yeah. So this might look tangential, but it's very interesting thing. So how many of you have heard about the liquid mirror telescope? Anyone? Yeah. So those who are in instrumentation would be very interested in this. So the left image is of the Devsthal campus of Aries, right? So the biggest optical telescope of India is in Devsthal, the top one. Maybe you can see the cursor as well. Yeah, this one. This one is housing a very big optical telescope, and this one bottom left one is where liquid mirror telescope was just started. Okay, so those of you who have not heard of this, so there are different types of telescope, but this one is a very unique telescope. I think one of a YouTuber has made a liquid mirror telescope by himself also. So maybe someone with enough resources can try that out as well. So what they do is take a dish of mercury or any liquid metal. I think gallium is also used, and rotate it very fast. So you just imagine when you rotate a dish of liquid very fast, it will basically, yeah, in this right hand side image, you will see side view of mirror surface. So you'll see that it will sort of take a parabolic shape because of the centrifugal forces. Okay, so this will basically take a form of a primary mirror, and now this will magnify the image or light that is coming from the top, and here electronic detector is placed and you can capture it. So why did I directly jump from the positional astronomy to this liquid mirror telescope? So there is one thing, if you see, for formation of this mirror, we had to rotate the base of the disk, right? Thin reflecting surface of Mercury, as it is written here, and rotating mirror platform. Yeah. So you can't have this platform in any other orientation. So what you need to do is have it like this, and it will rotate in this plane only. You can't have it rotating this way. Obviously, the liquid will fall off, right? So the only way to rotate it is keep it horizontal and keep on rotating. So the only place it will be pointing is directly up. Okay. So there is a technical term for that position, and that directly up position is in local coordinate system. I'll tell you why. And the name for that is maybe I've covered. Yeah. So the name for that is zenith. It's a special point in the sky. So any guesses? Let's see if some of you are already, I think many of you are already knowing of the term zenith, but if someone is able to work out, I'll like to know the answer of what you think the altitude and azimuth values are. If you don't know, you can use the app. So I'll give you the hint. Zenith is the point directly above your head. Okay. So any answers? What do you think? Yeah. Yeah. Any other answers for azimuth? Okay, yeah. So I won't keep on holding for too long. So yeah, as Arjun said rightly, the altitude value is 90 degrees. So as you go higher and higher, the highest you can go is 90 degrees. Okay. Let me see if I can quickly jump back. Yeah. Yeah, so no, okay, on this one. So the highest you can go is 90 degrees. Okay, it won't be apparent from this image. Now the problem is, what is the azimuth value? Do you know what is the longitude value at the North Pole or the South Pole? So if you have read geography properly, you would know that it's undefined, because you can walk on any longitude line and get to the North Pole or South Pole. So all of the longitudes converge at, like in this image, all of the RA lines are converging at the North Celestial Pole and South Celestial Pole. Similarly, the local coordinate system, all the all the altitude lines are converging on zenith. So there is no azimuth. So you can take any value, in fact. So any value of azimuth and altitude 90 degree will give you the zenith. So why did we take this example? Right? This is our second code, and it has to do with liquid mirror telescope. As I explained, that this liquid mirror telescope will only be able to observe one point, and that is directly above our head. Now there are many types of telescope. I think Arjun would know better that manual telescopes, you need to keep on aligning the telescope to different to that object again and again, because there is no motor in it, and because of Earth's rotation, every object will move out of the field of view. Same thing will happen here. Liquid mirror telescope, you won't be able to track a single object, and it's like just looking at the view of from a window. So you won't be able to point it anywhere. It will just look at the object that is passing through the zenith. Right now, that's a very interesting view. But yeah, with this limitation, the good thing is that there is no like moving cost or anything involved. Only the motor is moving. You don't have to move big telescopes, and the cost wise, relatively, it's a lot less. You can get a very big diameter of the mirror using this. Now I'll just paste this code in the example. Yeah, what is your doubt? Yeah, exactly. So it will only survey one part of the sky, that is zenith. So depending on your latitude, in fact, the declination, if you have understood the RA deck, it will basically is just like a CCTV camera. It will just, the stars will keep on passing in front of it. It will keep on recording, and it will be so much restricted along a single line. The line would be a declination line. So constant declination line it will follow. This is an RA deck. Just imagine the stars are moving. Just imagine, just look over your head. Just imagine you are lying in your cot in a village, or if you are not in a city, then obviously not many stars are visible. Just imagine you are out in a camp, bonfire or something, and you are lying and looking directly over your head. You will see throughout the night the stars will move, and the star right above your head will keep on changing, obviously. So same thing will happen with liquid mirror telescope. Now the code that yeah, I forgot to paste that code. I think you guys should try this on your. Okay, this code is even simpler than the one we had in for the Mars, right? I'll now I'm jumping to the my notebook. Right. Liquid mirror telescope. Okay, I have pasted it. So there are many things to look at here. Okay, has everyone pasted this and able to run? Okay, I see a couple of yes. So now this is even shorter code than previous one. What you see, again, we load the time scale from API. Then right now you will see this is tc.utc. So as Pranshu had asked earlier, we could give any date time. So right now I think this is in UTC, 20th of January and 2000. That would mean 8 p.m. But yeah, that this 8 p.m. is in UTC. So we'll have to convert it to Indian Standard Time. So forget that. So what next we are doing, geographic, is api.wgs84.latlon. So there is something very interesting that I can go deeper into, but we'll just keep it at that. WGS84 is basically the standard coordinate frame for the Earth. So I think GPS satellite use this. If you want to get into details, the Earth is not a perfect spherical surface. It's an ellipsoid, a geoid, as it is technically called. It is flattened or bulging from the equator. And so there are coordinate systems specifically for GPS satellite that model the surface of the Earth properly. So this piece of code is basically just giving you latitude, longitude. I think I've taken in this example. So latitude degrees is 22.5 and longitude degrees is 88.3. This I think I've taken this for Kolkata. So those who are not in Kolkata, you can change. Or in anyways, if you want to find for any other latitude, longitude, what you have to do is change latitude and longitude degrees here. So our observer is nothing but geographic dot at time t. So observer is the combination of latitude, longitude, and the time. So geographic dot at t. Obviously, this is just a variable name. You can keep it as Kolkata or whatever. I can write this as Kolkata as well, right? So Kolkata at t, and it will still run. And let me just print Kolkata. I can do that here. We'll delete this Kolkata. What is Kolkata? So you can see Kolkata is geographic position in WGS 84 coordinates, and the latitude longitude is whatever I had given. Okay. So this observer variable has to have two things: one, position and time. So Kolkata at t observer. Now, what is the position that we want to see? Observer dot from alt as alt degrees 90 as degrees 0. So I'll run this. You see, it's 9:51, 39. If I change this to 10, this does not change. If I change this to 330, still does not change, because as I said, the azimuth degree will not matter here. Okay. So you can play around, and obviously you now understand how to make a variable for a location, how to change it for time. Okay, now one interesting thing we can do. We can, I'll delete this, rather comment this, and you can do that also, and use ts.now. So I am running it now. Okay, now you can see the value is changing. I keep on running. Okay, just see. Every time I run this, the value will keep on changing, obviously, because the at 15 degrees per hour the sky is rotating, and correspondingly the object in the sky, or at the zenith, which is being observed by a liquid mirror telescope, will also keep on changing. So just I run it again, and you'll see it is changing because the code is ts.now. Obviously you can do this for static time, any other time that you want. Okay, so this is a relation between, yeah, so what we are doing now, we took the location, added the time, and from alt as we got a position. What is POS? In Python, you should always do this. So this is apparent ICRS position and velocity, right? So the distance is not of matter here, but what is of matter is that what is LMT looking at? What is the RA deck value? So the RA and deck value is printed here. So this is right ascension. Like longitude, it is measured preferably in hours, and declination is plus 22 degree. So okay, you can change this degree, and you will find out how it changes. The longitude degree won't, obviously it will also change, but the declination is what is more important here. I'll change it to 0 from the equator, what it will be able to see. So you see the declination is changing. So the higher latitude you are, so the higher the declination will be able to see. And in fact, if you know basic of astronomy, the pole star, the Dhruv Tara, there is a whole mythological story around it. That altitude of that gives you the latitude of your place. So if you're on North Pole, if I enter latitude as 90, it will be only observing. So if you put this liquid mirror telescope on North Pole, it will only observe pole star always. Okay, so this is one interesting thing to take away from this. Okay, so everyone with me? Any doubts till now? So this is what we covered till now. Altas, Aridec, Zenith. Zenith basically means the highest point. Any doubts?
Fine.
Okay. So moving on. Now we come to meridian. Okay, so this is also a very basic concept that is taught in geography, but not many are aware of it. So meridian is line joining the north and south. So if you are sitting at your home right now, just try use the Altaz app. So if you have it open on your phone, it will basically it's a compass also. So it is showing you the direction north south as well. So you have four different direction: north, south, east, west, and the line, yeah, line joining north and south is meridian line. And if you notice, the zenith is on that line. It's an important line. And now, yeah. So if you know AM and PM, AM is called anti-meridian and PM is called post-meridian. So the time that we are keeping, the M in that is actually meridian. So what happens is that as the sun rises, right now the sun is rising and it is left of the meridian, because east is towards left if you are facing south. So just imagine you are facing south, the sun is rising on your left, right? And it will as it is rising, the altitude is 0. You can refer to this second image. Yeah, it is also showing variation in the the height as well of the sun. We'll cover that as well later. But just look at sunrise. The altitude is 0, keeps on rising, and once it is at its highest, the shadow will be shortest. Then the sun will go down and it will set. Now, the highest point of this sun. It's important to note that it's not always zenith. So there is something called zero shadow day that we can cover on later. The shadow of any pole will be 0 only if the sun is at zenith, right? But what we are considering right now is meridian. Meridian is basically the line when any object, it's not only the sun. If you study the motion of all the stars and planets and any celestial object in the sky, it will rise from the east, it will go higher and higher, and at when it is crossing the meridian, it is at its highest, and it's called transit. So the technical term in astronomy for that crossing is called a transit of transiting meridian. So it will transit the meridian and then go down. So meridian is an important point. And the other thing you can see here is nadir. So zenith is altitude is equal to 90 degree. Nadir is what is called the minus 90 degree point. Okay. So again, this was important thing about meridian. And yeah, I was talking about AM and PM. AM is anti-meridian, PM is post-meridian. So the reason that time before 12 in the noon is called AM is because the sun is to the left of meridian line. Left as in before the meridian line. And after it has crossed the meridian, the sun will go down and it's called post-meridian. Okay. So again, a basic quick refresher for your geography. Because of the tilt of the earth, we have seasons. There are four important points that you would know from your general knowledge. The 4 points are March equinox, June solstice, September equinox, and December solstice. So this is referred to, so these 4 points are very important. And you can see in the second diagram here, the path the sun will take for these 3 different days will be very different. In fact, it will be different for all the days. So if you know the concept of Uttarayan and Dakshinayan, the sun will go higher and higher towards north when it's in Uttarayan, and days will get longer. And similarly, there is Dakshinayan as the days will get shorter. Okay, so this is a very simple piece of code. Let's try to run that. I'll paste the code again in the chat box. Yeah, I pasted the code and I'll run it on the shared screen as well. Okay, yeah. So this is a very short code, you can see. Everyone with me? Okay. So from Skyfield, import almanac. Okay. Now again, we load the timescale TS. We take EPH. We can call it anything. Yeah. So this is ephemeris. I think different examples use different thing. So by the way, all these examples are taken from Skyfield. Yeah, forgot to tell you. So the link I initially showed in slide, rhodesmill.org Skyfield. You can see all these examples here. So I've only taken from them. There are many more examples. So if there is time, we'll go through each one of them. Now, yeah. So what we did was, so these are the 4 important dates in seasons. So equinox and solstice dates you can find out using this almanac function. So what I did was take T0 and T1, 2 dates starting and finishing, 2023 and 1/1, that is 1st of January. The end date T1 is 12/31, that is 31st of December. T comma Y almanac.find discrete T1 T0 T1 almanac.seasons. So using this ephemeris, what this line is doing all the heavy lifting. This is finding the seasons, right? Seasons means these 4 important points from using this ephemeris between T0 and T1. So the output, and for output we do for via ti in zip it print via almanac.season event and ISO. So the time is in UTC. So yeah, the output you should also be able to see is vernal equinox, summer solstice, autumnal equinox, winter solstice, the dates and the time in UTC. Remember, this time is in UTC. If you want to do it in, if you want IST, you'll have to correct for that. Okay, you can play around. Obviously, you can change the date to 2026 for 3 years. Also, you can run. Okay. So you'll get the 4 important points for any date. So why is it important? Okay, the reason I took this example was because if you know, I have one application called Hindu Calendar. So recently I gave a talk on Panchangs and this Hindu calendar. So there is an important thing called precession of equinox. I'll just show that slide. Right. So we are not going to calculate or going into detail of precision of equinox, but you would be aware of the discrepancy in the Uttarayan dates. Everyone would have celebrated Makar Sankranti or Pongal, or there are different names in different regions on 14th or 15th of January this year. But the image you saw here, the important point on Earth's orbit was December solstice. The Uttarayan is supposed to start from this. So what happened that many people are still following 14th and 15th of January as the start of Uttarayan. So that is because of precession of equinox. Okay, so I'm not going into detail of that, but because of that, the what we call as Makar Sankranti is drifting away from the winter solstice. So for that, I had used this simple code. There is one thing to do. So basically, I think in one of the groups I shared how the equinox dates and solstice dates would keep on changing. So for example, you can also, I think some of you would have played around anyways. If I change it to 2100, let's see for the next 75 years what happens. See, there is an error I am getting. This is also important to note. You can also play around and see. What I did was just to see what would happen in 2100 AD. The error is ephemeris range error, and the description should be given at the bottom. Yeah. See, the
Ephemeris is 2050 only, no?
yeah, so the error is itself very helpful. Ephemeris range error, ephemeris segment only covers dates 1899 to 2053. So if you go beyond that, if you're trying to calculate beyond that, it could have shown you erroneous result, but the library is very well made and it is telling you beforehand that this DE421.BSP will have error. So what I did for that was, don't do that right now. If you change it to DE441 BSP, it's the latest, I think one of the latest models from NASA, and it's very, very accurate. I think it is accurate up to 10,000 AD. That is the range, at least programmed in that. So once you do that and run that, the file is 3 GB in size. So it will, if you run it right now with 441 BSP, it will first download the 3 GB of ephemeris file and show you the result. Don't do that if you don't have the bandwidth. Okay, so that is one interesting thing that we can play around with. So this, using only this bit of code, we are able to calculate the different points on the Earth's orbit. Wait. Yeah, now the output is back again. So this concludes our season section. So see how easy it is. With although yeah, the thing is just see right now we are going through the examples and code examples one by one. So obviously it might look like we are not learning much, but if you have this code, so as I told you, this notebook is very easy to play around with. So this is only for 23, but now you have a program that can tell you the exact instance of equinox or solstice. So there is one more confusion. So people celebrate equinox and solstice on one day, but that is not the case. Actually, it is an instant. What happens is that as the Earth is orbiting around the Sun, you'll see that it's continually revolving. It's not like it ticks around one day at a time. The rotation is what gives us the day, and revolution is continually changing the position of the Earth. Now, so the instant at which the Earth is exactly aligned towards the Sun or away from the Sun in solstice, or exactly parallel to the Sun on equinox, that exact instant time is also given in the code example that we saw. So it's of importance. It's of actual importance in astronomy. So if you need that, this code will actually come in handy. Or you can, as I said, you can play around and see how that will vary year after year. One interesting thing to do that is do it for 4 years and see how it is changing. The hint for that changes leap years. Because of leap year correction, in 4 year period or 5 year period also, you'll see a jump of a few hours and a correction after the leap year is there. Okay, so you can play around with dates and see how that is affecting all this. Yeah, let's move on to the next topic. So as I said, AM and PM, right? AM and PM is anti-meridian and post-meridian. So the special name to the event that we are given when the sun is crossing the meridian is called solar noon. It's also called local noon. So in the illustration, you can see the meridian is the north-south line. P is the observer. So P's meridian is the line, the arc going from north to south, right through the zenith, and P's horizon is basically the 0 degree altitude circle, right? Now, as the sun is crossing the meridian, what is happening? That as I showed in previous illustration, the shadow will be the shortest and the sun will be the highest, right? So this also a very interesting time, local noon. Okay, so this is also of importance. Why? Now, let me see. I have my emulator window running. There is very interesting thing. I think this is all school level stuff, but not many are aware of it. So right now, one thing I already covered, like in Kolkata and Mumbai, you know, there is difference because of longitude, right? So let me open this Zero Shadow Day app. This is also an app you should try out. So I open local, right? The location here set is Bhuj. Let me change it to Kolkata. I assume many of you would be from Kolkata, right? So today, the date set is today, January 20th. We see the local noon as 11:47. So for Kolkata today, at 11:47, the sun was highest. Okay, now I'll change the location to Mumbai and see what happens. It's 12:48, right? And 12:48 is like 1 hour away. So Kolkata and Mumbai are, you can in fact calculate with this. 1 hour difference is basically 15 degree. So 15 degree of longitude difference is there between Kolkata and Mumbai approximately, right? So this calculation is important, very important, and this is not only for sun. So there is something that you need to know. The atmosphere is one of the biggest enemies of astronomers. So I don't know much about radio astronomy. Obviously, there are noises from man-made sources in radio astronomy. But if you have ever tried to capture, even visually, you would know that light pollution is one of the biggest enemies of the night sky. Right now, even if there was no light pollution, the lower the object is in atmosphere, you will find atmospheric turbulences and any other effects degrading the data. So if you have so first of all, you know that you can never look at the sun directly or observe it directly without protection. But you are able to do that when it is very, very low near the horizon, because it has to pass through a lot of atmosphere. That's why we are able to safely look at the sun at sunrise and sunset without any protection. So it has to go through a lot of things. So similarly, for many objects, you have to basically observe. If you have to observe it through the telescope, it might have a lot of atmosphere it has to go through. So the best time to, just keep note of that, the main takeaway from what I'm trying to say, the best time to observe any object is when it is crossing the meridian, because every planet or star or whatever you are observing will be at its highest, like the sun, when it is crossing the meridian. So the time of meridian crossing is very important. So this example might seem a little longer, but this basically tells you the meridian crossing time of the sun, and but you can obviously find the meridian transit time of any object. I'll paste the code here. Yeah, the code is pasted. You can try it on your own. I'll run it on my notebook as well. Okay. Yeah. So I hope everyone would have copied. So yeah. So now this code is basically to find the solar moon, that is local moon, that we just discussed here, right? And I've already covered the importance. So this meridian transit is not only important for the sun, but for astronomical observation also. Keep in mind that if you study astronomy, you'll find that it's the best. Any object is best observed when it is higher up in the sky, because it has to go through less atmosphere. Okay. So this code, let's walk through this. So date time, Pi TZ time zone, sky field almanac, again WSG 84 north and east. Yeah. So this another thing I think I might have missed out on. So N and E is I think are literal constants that you can type and see. They are used to denote north and east west of longitude. Yeah. You have a doubt?
Yeah, that is, I pasted the code, but I'm not getting the solar moon time.
So what is the error that?
No, Alokji, the code that you have pasted is still that F. You have not pasted after the time events line.
That's what.
Let me check. Chat window. Okay, meridian. Okay, okay. Sorry. So I think part of the code was
Missing.
cut. Yeah, I'll paste it again. Wait. So I can't delete this. Ignore this one. Ignore. Okay. Okay, wait. It's not allowing me to copy so many lines. I'll paste the next part again. So this last line is meridian transits. Okay. How should I split this? Okay, I'll ignore this one as well. So this is the first part, right? This is the first part, and the second part is this. Okay. Yeah, the limitation of, I think, number of lines you could paste. So yeah, so you can look at the notebook now and make sure that you have copied and pasted. I had to copy paste multiple times, so I'm not sure how it is looking on your chat, but you should be able to. The last two chats that I sent should be able to complete this part of the code. Okay, everyone able to get that? Okay.
Yeah, we got it.
Yeah. Okay, now look at the code. So again, a lot many lines are there, but it's still relatively simpler code. So after all the importing, here the local zone is important, because till now we were only using UTC, right? GMT, that is Universal Coordinated Time or Greenwich Mean Time. Now we need the time zone of Asia, Kolkata, that is IST. So I loaded the time zone using this. So this is used as a string literal. So many of you would have, while setting up your systems, you would have seen this is the standard string that is shown. So this is one of the ISO standards to depict the time zone. For Asia zone, Kolkata is what is the official term for IST, Indian Standard Time. Okay, so now ts.now we have been using is the same thing. Just now we are using it along with the time zone. So zone.localize dt.datetime.now. Now is today's current time, midnight and next midnight. So what we'll do, this midnight and next midnight are basically local time. So if we replace the hour to 0 and 000, so time basically take today. I think right now it's 7:11 p.m. 1911. If you change the hour to 0 and minutes to 0, basically it is the start of the day according to English calendar. So midnight becomes 20th January midnight. Then next midnight is 12 in the night after that. Okay, we add one day after to the previous midnight. So TS, T0, T1. T0 is midnight 12, T1 is next midnight. Okay, again, we use the same lightweight D421 BSP, and Kolkata variable, I define it as again WGS84.lat long. I give the lat long. N and E are constants that basically, if you are in Australia, obviously you have to multiply it by south. So I think it's very makes it readable. But what it will be doing in background, let me just type and show. If I run n is 1. Okay. I haven't imported n. Let me just type skyfield.api.s. Okay, I think Skyfield, I have to import Skyfield. Okay, anyways, so what it would do is S would be -1. So it's very clever way of giving latitude and longitude. And instead of writing it as north and south, which we cannot do in numbers, S is basically multiplying it by -1. Okay, just an interesting observation. So, so now F is meridian transit of the sun at Kolkata. Okay, and what are the times? So meridian transit is event, but we have to solve it for 2 times, from and to. So T0 is midnight, and next midnight is this. And there are 2 times it will cross. So there is one thing like zenith, we had nadir in that image, right? Similarly, like noon, there is another transit that happens. It crosses that line again, but we are not interested in that. That is called anti-transit. So when during the night 12 or something, like 11:47 in the noon that you are seeing the sun crossing above the sky. Similarly, there will be a crossing at the night time. So we ignore that, and we take from this times the one we are interested in and print it. Okay, t equal to time 0, t str string. We convert it to string, t dot as time zone and solar zone. Okay, so basically we have gone through all the code, and this is what I think. Yeah, so the same time we observed in the emulator as well. Okay, this is Mumbai, but let me change back to Kolkata. This is the same time. So the seconds are neglected here. You can see the same time we got for Kolkata. Now I'll click this basic, move this to advanced thing. So why is 12 o'clock not the solar noon time? So what we consider, all of us consider as noon is 12, right? 12 is noon, and after that is afternoon. But that is not the case. For Kolkata, we saw it as 11:47, and Mumbai is different. So many of you would guess that it is because of the longitude. So that is partially true. So all of our clocks are synced to the Allahabad standard Indian meridian, 82.5 degrees of longitude is what all of us follow. So all of our time zone is same. That's why because of that, the local noon time is not 12 for everyone. If everyone keeps their own local watch, then that way the local noon supposed to be at 12. But yeah, because of longitude, you can see the shift in Kolkata's local noon time is this. But what if I change the date? Here I can change the date in the app, and you can see there is this yellow bar at the bottom changing. This is something called equation of time, and this is because the Earth's orbit is not perfectly circular, and it keeps on speeding up and down in its orbit because of Kepler's law. So we won't get into that, but these 2 things are kept to be kept in mind when you are talking about local. Okay, again, just do one thing. We'll again do this for Mumbai. Can anyone tell me what's the latitude of Mumbai? Yeah. Anyone quickly do a Google search, or maybe I can also do it. Mumbai. Okay, 19 and 73 crudely. I'll just do them 19. I'll change this to 19 and 73. Okay, so this is not Kolkata now. I'll change this, otherwise there will be confusion. I'll change the location to Mumbai and run the code. So you can see it matches with the app as well. Solar noon for 20th of January is 12:48. So obviously this is code, so you can do this for any place or any date. So now you have calculated the local noon time for Mumbai. Yeah, I can undo as well. Okay, so I've undone and I'm back to the Kolkata thing. So this is the way you calculate solar noon time. So meridian transit, just see. Right now what I did was for sun, but as I told you, this meridian transit you can do for any other object in this ephemeris database. Okay, you can do that for Mars or even any other stars. Okay, now moving on. Any doubts till now?
Very clear, sir. No doubts.
Okay, okay. So this is the code that we have already covered. Now we move on to sunrise and sunset. So this is one more app that I think you can download and try. But there is a couple of things that I'll try to show in this 3D model. I'm not sure how clear the location has to be changed. It's mountain views. Manually, I'll change it to Kolkata. Yeah. So now all of you know sunrise and sunset. So there is a lot of issues in how we are taught about sunrise and sunset. We are taught that sunrise happens in the east direction and sunset happens in the west direction, which is not exactly true. So I'll not go into deep details about this, but Uttarayana and Dakshinayan is also applicable to the rise and set point. So it's not exactly east and west where the sun rises. You can actually look at it in this 3D view and see for your location or any other location, you can see where the sun is rising or setting. You can change the date and play around with the time, right? So you basically rise and set points depend on the which day of the year you are in. Now, why I mentioned this app was there are 4 important terms to see. I think the color is not very good here, so you might have some issues. So let me just open it on. Okay, I think the Chrome just crashed the emulator. Okay, let it be. I'll show it here. Twilight Wiki. Oh, different highlight is shown. Okay, so what I was trying to show in the emulator will try to cover here. So there are 4 types of sunrise and sunset. Okay, so the only one you would have been aware of is only simply sunrise and sunset, but actually there are 4. So one is called official sunrise, official sunset. The other is civil sunrise, civil sunset. Then nautical sunrise and nautical sunset, and astronomical sunrise and astronomical sunset. Okay, there are 4 types of sunrise and sunset. What do they correspond to? So basically, I've opened the Twilight Wiki article. You can also open it on your, if you're not able to see it properly. I'll try to zoom to the image. Yeah. So if I do have any images. So what happens is that when the sun is rising, or rather when right now, if you consider how the sky is outside, once the sun has set, that means the altitude of the sun is now less than 0. Still, it's not completely dark. What you call twilight is still visible, right? So it will get completely dark when the sun is a certain altitude below the horizon. So first of all, the definition of rise and set is when the sun is rising, when the sun is coming up and its altitude is 0. I'm doing a lot of approximations here because there are atmospheric factors and other things that need to be considered. But just crudely, when the altitude is 0, the sun has risen. In the western side, when the altitude is 0, the sun is setting. Okay. Now, the other 3 types of sunrise and sunset depends on these 3 altitude values: 6 degrees, 12 degrees, and 18 degrees. So when the sun has set in Kolkata at 0 degree altitude, that was official sunset. Then once the altitude of the sun was 6 degrees below the horizon, which means minus 6 degrees in the western side. Then it was civil sunset. Okay, then it went down further, and it went to -12 degrees. That is nautical sunset. And finally, when the sun's altitude was -18 degrees, then it was astronomical sunset. So astronomical sunset is what we consider a complete darkness to set in. At that altitude, the sun's light will not be able to refract around and be able to brighten up our atmosphere. So we'll have pitch black, supposedly pitch black sky. At least no sunlight should be able to directly come in the atmosphere. So for astronomical purposes, the night definition of night starts from astronomical sunset. And similarly, there is rising. This, I think I was showing the rise here, but yeah, the same thing happens on rise. So -18, -6, -12, -6, then 0. The sun goes up, crosses meridian. Then after sunset, 0 degree, -6, -12, -18. So this is all about the concept of different types of rise and set, and the period in between is called twilight. So this whole period is together is called twilight, but they are subdivided into civil twilight, nautical twilight, and astronomical twilight. After astronomical twilight, you see there is night. Okay. So this is an important thing to calculate. I think, yeah, the app I was showing, emulator just crashed, so I won't be able to show. If you have your phone, you can try out the app, and it will show you the all these timings. So in a day, first of all, we'll get astronomical sunrise, then nautical, then civil, then official, then transit. Transit is of the meridian, then official set, civil set, nautical sunset, and astronomical sunset. Okay, so our next example is this. When will it get dark tonight? Already, it's, I think after our talk started, the sky would have gotten darker. But so basically, we'll be finding all these sunrise and sunset values. So this is the code. I'll paste it here. Okay, wait. Kolkata F. Yeah, sorry. So copy paste this one. Ignore the F. I'll paste the F part again. Again, the code is slightly larger. Yeah. So this is how the code will look. Just keep sure of this one. So this is where the line break in my comment where I pasted, and this is the output. Okay. Again, this is for Kolkata. Everyone with me? Everyone able to follow?
Yes, sir. I got it.
Okay. So yeah. So same thing here. We have defined our in IST. Now we take midnight, next midnight, because we are concerned about the time between for this date only. We take T0 and T1 as midnight and next midnight. Kolkata is defined the same. I think most of the code initial part is the same from previous one. Then from almanac function, we do dark twilight day, and using ephemeris and location Kolkata, we find all the times for that events. Okay, this basically this is tuple. This is called a tuple in Python. You can read up on that in Python. So basically, we are getting two return values. The same thing was happening in previous examples also. So the return values is times as well as the corresponding events. Okay, now what we do, we take iterate over the times and events together, and we print the timing and corresponding event name. So E is, I think, the index used for that. Almanac.twilights is an array. Generally, the convention is the all caps is used for a constant. In this case, the constant is an array of the names of twilight. So yeah, so you can, I think you can do this also. You can just paste it here and play around. See, this is just a dictionary, right? Almanac.twilight 0, 1, 2, 3, 4, night, twilight, and day. So it's looping through that, and it is telling you whether it's start or end, right? TSTR, depending on whether it's less than E or not. So this is the code. Now for Kolkata, you basically have all the values: the sunrise, astronomical sunrise, nautical sunrise, civil sunrise, official sunrise, then official sunset, civil sunset, and nautical sunset, and astronomical sunset. So this example, whatever my app, the sunrise sunset app was showing, you are able to do this with the same with this simple code. Okay. Okay. So I thought of covering zero shadow day as well, but let us skip that. I did not include that. Also because that would have meant slightly more work on the in terms of code. So zero shadow day one can calculate using this library. In fact, the zero shadow day tool that I have made this tool. I think app was recent, but there is this website that I had made. I had used these sort of calculations 7 or 8 years back. So the basic idea is you get the solar declination. So the RA deck that I told you about, the every day the declination of the sun keep on changing. That means it is either going north or south. So its position in the sky changes daily, and there would be a day when locations between tropics will see the sun passing overhead through the zenith. So that is the day of zero shadow day. So we can use this code, this library to find that also. But I'll skip that. So that will involve a lot of explanation. So I'll just skip that and move on to one more example. So this example, yeah. What's your doubt?
This zero shadow day will appear when the declination matches exactly our latitude. Am I correct?
Exactly. So the code will go about that only. So what you can do is, I would have written a for loop. So every day of the year, you can just check whether the declination of the sun for that day equals your latitude. If it is equal, then that day is zero shadow day. So there is some technicality involved, because what will happen is that it will basically cross that value. It won't be exactly equal. So declination. So your say Kolkata latitude is 22 degree, right? So near the solstice, it will come to 22 degree and cross it on a day. It won't be exactly equal. So the day it crosses, you can just check that in the code. That is how I have even implemented in the app and tools. So yeah, the basic idea is it is equal, but practically what you have to do, because you're not calculating declination for every time instant, right? So it's simply a matter of when that declination will cross that latitude. Yeah.
So it means that any location beyond the Tropic of Cancer or beyond Tropic of Capricorn will not have a zero shadow day.
Yeah, exactly. So Delhi will not have it, and any line, any place with above the Tropic of Cancer will not observe the zero shadow day. On solstice day in northern hemisphere, the shadow will be shortest. So the sun will be. We are talking about summer solstice. So in northern hemisphere, the sun will be the highest it can be throughout the year. That is all. But in tropics, what will happen is it will go higher and higher, and after the zero shadow day, it will move towards the northern part of the sky. Let's skip that because I don't have images to explain that. But yeah, your thinking is right, in right direction. Okay, so this is the final example that I have prepared. Okay, phase of the moon, Tithi. So now the sun and the moon are basically going around in the sky, right? Now, because of the tilt of the earth, we saw in previous images, the sun is not going it is going in a straight line, but it is not aligned with the celestial equator. So because of the tilt of the earth, every day that path the sun is taking keeps on changing. You can use the sunrise sunset app to, or the ZSD app, to see how that path changes every day. Okay, so the path the sun takes in the sky is called the ecliptic. Okay, now very interesting thing, all the planets, all the solar system objects, most of them you would see are very close to the ecliptic. Why is that? Because the solar system is planar, more or less planar. So there are slight variation in tilts of all the planets, but more or less, if you see any textbook illustration, you will see that एक ही plane में है. They are like a jalebi. All the orbits are basically in the same plane. There are slight variation in each of the tilt. Now, because of that, what we see is all the planets that we are able to see in the sky all fall in near that ecliptic. So that's why there is one more coordinate system called ecliptic coordinate system, I think that will be used here. So you see in this image, let me make it full screen. Yeah. So you see in this image, in Western terms, we call it waxing and waning phase of the moon, then gibbous full, crescent, and all these are English terms. So correspondingly, in Indian culture, we have tithis, right? So we have Shukla Paksh and Krishna Paksh in lunar calendars, which tell us whether the moon is increasing in size or decreasing in size. Now, and correspondingly, the days are numbered based on the phase of the moon. So this is called tithi. Now, how to calculate tithi? So if you're not calculating tithi, the Western term for that is illumination percentage. So the corresponding mathematical term for that. So you can see the new moon. Here is the new moon. It is 0% illuminated. You can't see the moon. That's why it's because it is not illuminated at all. We are not talking about the moon being set, right? So over a 24-hour period, you can there will be a moonrise, there will be a moon set. So even if the moon is in the sky and still you are not able to see, first of all, it will be very near to the sun. That's why it will be difficult. But anyways, if you could block the sun, still you would not be able to see, because all the surface of the moon that is illuminated won't be facing us. So that phase will have 0% illumination, and the full moon obviously will have 100%. So in between we have this cycle. When the illuminated part of the moon increases from 0 to 100, we call it waxing or Shukla Paksh, and the other is waning phase or Krishna Paksh. Okay. So how do you go about calculating this phase of the moon, right? So the final example I have prepared is, what phase is the moon tonight? So I'll paste that code. Let's see if it is okay. Again, lines are cutting. I'll paste it in two parts. First one is this, then the second one is this. Yeah. Okay. Now you can copy and paste. I'll also do that on my front. Okay, so working. Yeah, so okay, now we have what we are doing here. Again, a time scale loaded. Right now, I think I have this is for 2019. So 19.0, I estimated that this example would come near 7 p.m. So 19.0. Okay, yeah, but this is in UTC. Again, we can do that ts.now. We can change that too. Let me do that. We'll change the percentage as well. Yeah. So yeah, this is the current time. This is loaded off. We have loaded ephemeris, sun, moon, and earth. So we need to load all three ephemeris of sun. Basically, we are initiating the variable sun and moon and earth. E is earth at time t. S is the apparent position of the sun as observed from earth at time t. M is the apparent position of the moon as seen from earth at time t. So this is very apparent. So sun, moon, earth are variables that are simply the objects, and once you observe them, they have a position. You can just look at it from here. So if I enter sun here, sun is a Chebyshev position. So very technical term, but just ignore for that. If I do S, it is apparent GCRS position. Okay. So there is a difference. So one is an absolute position, and once you involve the observer point in time, then it's the position, actual position in the sky, S and M. So what is this? What we'll do, and what we'll do is we'll shift this to ecliptic coordinate system. Depending on the, there are a couple of images. I think I could have added them in the slide, but basically the phase of the moon will tell you how far it is away from the sun in the sky. A full moon means it is exactly opposite to the sun, right? In the, as you can infer from this diagram. Although this diagram is from outside of Earth and space, but in the from as observed from Earth also, the bigger the moon is, the farther away it is from the sun in terms of angular separation. So that is what basic idea of the or the percentage elimination is. Okay, now where's the, so what we do basically for S, we calculate the coordinates in ecliptic. right? Ecliptic coordinate system is basically just like RADEC, just it is based on the path of the sun. Because it is tilted, it's slightly tilted to the celestial equator. Otherwise, it is similar to RADEC. Now, two values will be given. One is latitude and longitude, ecliptic latitude and ecliptic longitude. Okay, so the technical term for that is, we are not interested in ecliptic latitude. We ignore that. And same for the moon. What we do, underscore is basically, if you're not aware, in Python there are two parameters being returned here. So underscore we just ignore. We can assign it another variable, but we are not using in this example. So underscore is basically discard. So we are discarding the latitudes and storing sun's longitude and moon's longitude in this. Okay. So the moon longitude in degrees minus sun longitude in degrees, percentage 360 is phase. So it is 341.6. We can do tithi also. So what we can do is long minus percentage. See, now the difference is, this is the angular difference of the position of the moon and the sun along the ecliptic. If I divide this by 30, okay, I'll have to normalize it anyway. So this is percentage. First of all, what is the difference? Minus 18 degrees. Okay, so I'll have to take the absolute value. Yeah, okay, first of all, let me check what is the tithi right now. It is Chaturdashi. Okay, so what this means is, if I do it percentage 60, okay, yeah, it's the same phase, 360. Yeah. So okay. So basically, each of the tithi is spanning the 360-degree difference between moon and the sun. So I'll not confuse. I think a couple of you are interested in finding this. So if the difference was initial 30 degree, then it would have been Prathama. So I think this is the last 30 degree, 360 minus 30. So this will come out to be Chaturdashi, right? So it's simple division will give it in minus. So it is just before 360. It means it is Chaturdashi, right? If it was 360 minus 30, if it was before 330, then it would have been Trayodashi, and that way. So that is how you get the tithi. So we just ignore that. We are using just the Western counterparts of that in this example. So the phase is given in percentages, and the percent illuminated, it is giving the how much of that is in terms of percentage illumination. So Chaturdashi Tithi, and today is Krishna Paksh. Yeah. So after 14 days of full moon, 14 Tithis of full moon, the moon is diminished so much that it is 2.7%. I think Amavasya is about to come. That means this illumination percentage will drop down to 0, then keep on increasing again. And the phase angle difference will again circle around and start again from 0 once you take the this absolute value in 360-degree scale. Okay, so this wraps up the all the examples I have. So any questions till now? So okay, so let me just direct you all to this website. So this is the Skyfield website. This is a table of contents you should all go to. So I've taken all the examples I've taken were from this part only.
Can you give the that link on in the paste?
Yeah, I'm pasting the link. Yeah. So there are a couple of more things that we can do, but rather than going into its concept, because they they are even more advanced. So, and there are some problems. Even I was getting some problem in plotting them. Let me see if I have them ready. So yeah, so the code that I had ready, I'll open it on my end. This will be of relevance to others as well. Let me just run it here. Okay, this is not changed yet. Okay, so yeah, everyone with me now. I'll try to cover this example, but till now, do you have any doubt? Yeah, so there are a couple of advanced examples given in this. Where is the website? Yeah, in this example here. So almanac computation example. So if you go to example plots, this is where matplotlib will be useful. So I'll open the first one, charting and apparition of Venus. So you can see the local coordinate system is used here, altitude and azimuth. So Venus moves around very fast in the sky because it is an inferior planet. That means the orbit is smaller than the Earth, and you can see its position changing very fast. Jupiter and Saturn relatively are moving slower in the sky, and so this example code is basically plotting. The example is of older dates, but yeah, we can change it and run for current time period. So from April 2021 to January 22, what is the where would you find the find Venus in the evening sky? So this is west direction. You can see how the plot is changing. Okay, so here is the code. You can it's very long. I wouldn't even bother to copy and paste it in the chat box. I have given the link to this TOC. Let me just give the link to the this example also. So this is a very advanced example. So those who are interested can go through this and try it on your own. And yeah, so this is the link I have given recently. So this is the first plot. This is how the Venus will look. Obviously, this is for 2021 and 22. You can see the code is very long, but you will get an idea. First, you'll have to change the observer. I think the observer lat long is plus 40. So it's obviously for US or Canada or some other place. You can change it to your location, and the starting and end date, you can change it to. Let me do that myself. That would be a better thing. I'll do that for Kolkata. Right, so this is I think 22 and this was 88 something. And instead of 23, I'll start from this year and we'll see how it goes to the end of this year. Observer lat long. Okay, this is again gone 88. Let's see if it is running or not first of all. 40° north. So why is it showing 40? Yeah, okay. So this text needs to be changed. 22. So this is just a title. We can change it together. January 22. Oh, sorry, 2023 to December 23. If I run it again, in fact, the image is being saved as a PNG. If you run this code, copy it from the website I have given, it is also generating the image as well. So that's why the code is a little bit more involved. Yeah, so this is how it will look for 22° north. January, and it will go highest in April, and it will in July only it will set. So from being a evening star, I think it will shift to being a morning star. We can do that also. Right now, I think it is showing west. If we somewhere we can change the azimuth range, and it will show that it will be visible in the morning sky in eastern direction. So this image we can generate for morning also. So this is one example, Venus. Then there are many more examples. I think satellites was something I wanted to cover, but it would have involved even more technical discussion. So you know of some apps which show the ISS and other satellite viewing time. So you can use this library to calculate the positions of satellites also. I think the relevant section is this one, Earth satellites. Yeah. On the same website, the one that I shared, you can play around with all the examples and sections that are given. So we are not going into the satellite one. I wanted to do the other plot one that is more relevant, and I think all of you should at least keep an eye out for that. So the second example given here is Comet Neowise. It's an old comet. The example is old. I've given it in the chat. So for 2020, it is showing the how it is moving along through Saptarishi. So those who are familiar with astronomy, you will see that this is basically part of the Saptarishi constellation or Ursa Major. So how it moved through July 2020 through this. So you can generate this plot. So there are some issues with this library, and that's why I didn't go cover this one. I'll have to change the code a lot. So I had played around with this. I'll copy this code. You can also copy, but it will not work. There are a couple of changes to be made. I'll do that right now. So first of all, I'll have to remove this thing. So basically the constellation lines that you see here, this one, the lines are being downloaded from a GitHub file. The problem is the format that they were uploaded in has changed. So that won't work. So what I'll do is I'll just comment this. Okay. This is commented. So this will now work for NeoWise, but we are not interested in NeoWise. What we are interested is in ZT, yeah, this one. C 2022 E3 ZTF. So that's the official term for this comet. I think you should keep an eye out. It will be near Pole Star. Many people have captured it already in the morning sky. So it's a beautiful sight. Hopefully, we might see it as a naked eye comet. This comet name C22 2022 E3 ZTF. Now I'll try to change the code. Let's see if it works or not. I'll try to change in my notebook. See what is happening. The code is long, but I'll change it. So time zone, time change for comet is 2020. I'll change it to 2023. 7 is month July. I'll change it to January. Range 1 to 31. So 1st of January to 31st of January. Then the name, the comet database. I'm not sure whether it will take or not. I'll just try. So this is the official name in the database C/2022 E3 ZTF. If it will work, then that means it was in the database. Then what needs to be changed? Color and location, NeoWise. This is not NeoWise. This is ZTF or whatever E3 ZTF. Let's call it. Right now, and yeah, location. I think I have to change the location as well. Field of view, projection, lower row, comments. Wait, I think it will be at the bottom. Okay, yeah. So, anyways, independent of the location, we want it in array deck. So, location is not important for chart. Okay, okay, yeah. So, comet NeoWise. This is not NeoWise. This is E3 ZTF. Okay, so some changes in the code are required, but you can see now we have generated the plot. The problem was the line files we couldn't download. There is a problem in the format, so it's not that beautiful. But you can see the comet's path in the sky, and the this matplotlib is being used to plot the stars as well. So I'll show a better path in the sky. I'll show a better image. I think Earth and Sky telescope has plotted it better. Yeah, this one is also fine. So yeah, this is image you can share. It's how to see. Yeah, so this is the path. In fact, they are only concentrating on the last 5 days, 20th of January. So just remember, today is 20th of Jan, and next 10 days it is supposed to get closest to the Earth, and hopefully, if it is bright enough to be seen with the naked eyes, everyone can try to watch this comet. So it will be near Pole Star, Dhruv Tara, and so the plot that we just copied, we changed the code to calculate the path in the sky from NeoWise to E3 ZTF. Okay, this is the path right now. Actually, it's not much of use because I'll have to change the dates because the relevant dates are going out. I'll change the dates quickly to from 20th. We are relevant. We are interested in the next 10 days. Okay, I'll run it again. Hopefully, it is now it is fit. Okay, so same, we are able to see, unfortunately, the lines are not visible. I'll try to see if I can get this work. So you will be able to generate such beautiful illustration by yourself. Obviously, the code is slightly more advanced, and if you are up for it, you can use this Python code to plot and chart the stars as well. So this was an interesting, relevant example. That's why I covered comet. Otherwise, also there are ways to use this. So if you are interested in, say for example, you are a radio astronomer and want to make an illustration for a radio source in the sky, you can use this code quickly to just make an illustration for that constellation and show your radio source. So that way also the database, star database that is being used here can be used to make illustration. Let me show you one thing. So yeah, so you can make something like this also, although this is on my website. Okay, I forgot what was the name. Let me... Okay, so it's not .html. Yeah, so this is just a test chart I made. So this is current sky. Okay, although this is not Python. Okay, so this is today at this instant the sky overhead. So you can see Jupiter and Neptune, Mars, and all the constellations. The labels have been turned off. This is I have written this in JavaScript. This is using a charting library, so I have not made this from scratch. So similar thing you can use if you want to in Python. So this, for that you need some mastery in Matplotlib. So I did not cover this in detail because this would involve first of all learning Matplotlib, and you can see all the code is there. So the link that I sent you last is basically to this one only. Yeah, after the Venus one, at the same page, yeah, you can find the NeoWise chart. The final example on this page is plotting satellite altitude during re-entry. So again, if you are interested and you know about orbital dynamics, so this is one other example that you can cover. But I'll not take this. Take that. So we'll wrap up with this one. So this is basically the path of comet that you should look out for in the coming week. So we have, I think, covered 6 or 7 examples. I have pasted them, most of them in the Google Meet, but I have already compiled them in a single notebook, and I'll share that right now. Can I share a file in the Meet chat box, or how should I share it?
You can mail that, and we'll just mail it back to them, everyone who has registered.
Okay, so I'll mail that file. So all the examples till now that we have covered in this notebook, I'm not going to send this one. The first 6 example. Let me just bring that notebook. So I was copy and pasting from this screen actually. Yeah. So all the sections are also marked. You can see how the sections were there. So you already have all this code, but still this is a single source. Maybe you would have changed. So this is the original Astronomy with Python notebook. I will send this as a mail. So these are the 6 examples covered. But I encourage you, like you saw in the live demo, I played around with the different parameters, and just you can see which parameters. Even this library is new for me. The library I used to use in Python is deprecated now, so I'll show that as well. So I have taken a couple of workshops in Python with Astronomy. So this is the library I have been using till now, PyFM. So it performed pretty much all of the same things, and I in the workshops I covered similar concepts that I covered now. But the problem with this is it's deprecated because with the Python 3, the programming paradigm is now more functional, and the best practices that are to be followed were not followed in this PyFM. It's very heavy and very how do you call it? Very old-fashioned library. So the same developer, Rhodesmill, he basically rewrote this and shifted to this Skyfield library. So that's why I chose this library to start off with. Otherwise, I have a lot of old code lying around that was written in PyFM, and I used the workshop for that. But I would encourage you to use only this. And as you would have seen with the examples, you can go through the website. With minimal of effort, you can calculate a lot of things, and if you are good at Matplotlib and figures, you can generate actual useful illustrations using the same Python code. So with that, I think I should wrap this talk. I'll obviously, I think you'll have questions, so we can have that discussion now. Yeah. So any questions?
If anyone has any question, they can open their mic and speak out.
Yeah.
Alokji, though may not be in this session, it was very nice. In the subsequent session, as uh, we have been told that we will have part two of this with some advanced topics and other things. I want to learn from you about the equinox, precession of equinox, and the effect of nutation and equinox on on the positions of the planets.
Okay. Yeah. So for me also, this is a new thing. If you remember, I shared this change in equinox data in that group. Okay, maybe you were not in that group, but
I'm there. I'm there. I had.
yeah. So for others who were not aware, so I recently took a talk on Indian calendar, basically Panchang. So there is a discrepancy in Panchangs because of precession of equinox. The Earth is rotating like a top, and that precession is causing the seasons to drift in terms of the festival. Like best example being Makar Sankranti. It is happening to other festivals also, but Makar Sankranti is supposed to be observed at the start of Uttarayan, that is winter solstice. So what he's referring to is how can we use this library. So in fact, I after that at that time only I saw the example code, and I used the heavy ephemeris file I was talking about, and I calculated the equinox timing, solstice timing for 10,000 year period. Now, yeah, I also have to, as you said, basically it's a research for me as well. I'll give some time, and we can use that library. Remember the ephemeris library for that is de441.bsp, right? So that is the heavy one, 3 GB file. You will have to download that. It will download it automatically. So if you are using that, then it allows you to do ephemeris calculation, that is positional calculation for I think 10,000 year period, 10,000 before 10,000 BC to 10,000 AD or something similar. So yeah, you wanted to play around with precession values. I'll also do the same. So the code is all here. So right now in the workshop, we have made everyone aware with the tools. Now it's just a matter of us to write the code and see what we want to see the variation of. So precession of equinox, if you want, again, the problem with Ayanansha is the Lahiri or Raman or whichever Ayanansha you want, that is like an standard that you'll have to see. So that you won't find in this library. This will tell you the absolute ecliptic in the ecliptic coordinate position of all the planets, sun and moon, and you'll have to see the Ayanansha value on your own, which are being used in Panchang. But yeah, if you want to see the variation in the precession and nutation, this library is the way to go for that.
Okay, thank you. And I would be very much interested in that topic, and we will interact on this topic later.
So
But
even I am pursuing research. You can say even I am a researcher. We can
yes,
see how that is being affected. So we
yes.
know that precession is affecting, but you have to play around with what is the exact value of change and over a period of tens of thousands of years.
And even delta t value is also changing. It is not constant.
Yeah.
So there are different algorithms are taking different delta t. We
Yeah.
have to, because of that change, there is a change in ephemeris also. What
Yeah.
Postal Astronomy Center uses, what Swiss ephemeris uses,
Yeah.
what NASA uses, the change is because of the delta t.
Yeah, but
Maybe
no,
it is
here you can get the most accurate one. So DE441 is the most. PAC, the problem with PAC is I showed the site in the beginning. I couldn't find historical ephemeris data. And I'm not sure which ephemeris model they are using. So maybe if we can dig
Swiss ephemeris. I
Swiss
was told
ephemeris.
earlier the Swiss ephemeris there.
So did you get this directly from PSC or?
No, earlier
I'm
I had
talking
one
about
person.
PSC, the government body,
Yes, yes,
Postal
Postal
Astronomy.
Astronomy Center, Calcutta.
Yeah, so they are using Swiss ephemeris.
They are using Swiss ephemeris based.
Okay, so that is yeah. So that algorithm is also more crude. So the one we have been using D421, I think it is along the same accuracy. There is a bigger file version of that, but the one I'm talking about, it will be even more accurate than Swiss ephemeris, DE441. So you should try that out. Google for rather than
DE441.
yeah, I can. I have the screen shared right now. I'll just close this. You can DE441.bsp. Yeah, 441. The JPL planetary. So yeah, these are research papers that are telling us about how much accurate they are. So let me see if I have a better JPL planetary lunar estimates. Yeah, so this you can see, yeah, different, yeah, now you can see on my screen different ephemeris being listed. So this was the one we have been using, DE421, includes nutations and librations. So it was covering that, but the range is, accuracy range is very small. Similarly, 422, uh, it's, oh, sorry, I was talking about 441. Yeah, 441 is minus 13,200 VC to 17,000. But yeah, remember, corresponding file is also 3 GB. So I have it downloaded on my PC. That is the one I use for calculating the equinox and solstice date in the future. Yeah. Okay, next question.
Thank you.
Yeah, any other? Hello. Yeah, any other?
Yeah, I had a question about the code that we did for calculating the telescope the time continuously. We observed that right ascension and declination both were changing in that, but shouldn't be the case that the declination should not change in that program.
How much was the change? I don't remember the value of the change. You're talking about changing of time only, na? Not latitude.
Not the latitude, just when it was we did UTC now, and when we ran the code every second, the
You're talking
right
about
ascension
LMT
was
one, right?
changing.
Zenith. You're talking about Zenith one, na?
The Zenith one.
Yeah.
So
So
in that
again, yeah, I was also surprised. The thing is, this is taking very accurate WSG84 model, so the geoid model. So because of that curvature of so departure of the Earth from the roundness, because of that also some variation would have been considered. So I think that is what is being causing the change. It shouldn't be much. I think it should be less than half a degree of value. I think.
it
Uh,
was way less than half degree.
how much was the change?
It was varying in point zero 1 degrees, I think.
Yeah, yeah. So since this is zenith, atmospheric variation is not the reason. The reason is the uh, geoid thing. So I was also surprised that there was small change, because considering Earth as a perfect sphere will directly give you that latitude equal to declination. But yeah, if you use this will take into account the deformation of the Earth. So yeah, that would be the reason for the slight change in value of declination.
Okay, thank you.
Yeah. Any other question? I think there was one hand raised. I think it has gone down now. What was the name of the person? Any other doubts? Yeah. Yeah, you can ask anything. So yeah.
Okay, first of all, thank you for this amazing session. It was very informative. So I had just a basic question. Like, if you, I don't know if you have mentioned where to get the source of the data. I wasn't present the whole meet, so can you just repeat to like I would like to tinker with this data set and see how it goes.
Yeah, so the data set is in basically the ephemeris from NASA. The latest one, I have the screen I have shared right now. It is showing all the ephemeris libraries from NASA directly, and they the way this happens is that this is JPL NASA's website. They make these ephemeris libraries, and they are directly used in different space missions. So the one Mangalyaan is ISRO's. I'm not sure which ephemeris they are using, but Cassini and all other planetary probes that were launched by NASA, they are actually using these ephemeris. So they are actually accurate to meter level accuracy. That's why they plan the approach of the satellites and the rover landing and all that. So the one we were using in most of the example is DE421 Let me just scroll up. You can basically, these are all different models. You can see here DE421 is this one, created on Feb 20, 2008, includes mutation liberations and all. So let me give you some code examples. So if you were there in all the code examples, you will see ephemeris file being loaded. For example, this where is the first example, Mars location. This is loading a DE421.bsp. So if you run this file, once you have Skyfield and everything installed, this file will be downloaded to your computer automatically. You don't have to do that. Now, the accuracy range of this is only 2000, 1899 to 2053. So if you are doing some calculation for right now, it's more than enough. It's a 16 MB file. You don't even need to open that file to look at it. It's all binary data anyways. So what I was discussing about was research oriented, that how the precision of equinox is affecting all this, how the seasons are varying throughout tens of thousands of years. In fact, I also recently learned about this, how the climate is changing. So climate scientists are studying long-term changes in climate of the earth. So ice ages are happening over tens of thousands of years. Why is that? Because Earth's tilt is also changing. The precession is causing the Earth's axis to wobble. Then there is nutation, like slight wobble in the axis value, and orbit is changing. So many parameters are changing. I think it's called Wilkovich cycle or something. So because of all of that, Earth periodically goes through different ice ages. So that study, if you want to do, you need a long date range. So for that, this data set DE441 is needed. So I also use that. So that this is what I was talking about. 3 GB file is this one. So if you change the example here to DE441, in all of the examples, it's not needed. But if you need accuracy over a long period of tens of thousands of years, then use that. So the way to do that is just line. So this library is so good that to use the latest NASA ephemeris, whichever NASA ephemeris library you want to use, just use this load line. So changing this will change the library, and you can choose the ephemeris based on your requirement.
Okay, got it. Thanks a lot.
Yeah. Any other question? And we are just about 8 after 8. So we are 8 minutes over time. I was doubtful how much time it will take, because there are many examples, and I think that for many of you, at least some of you, these concepts were not new. But those who are new to basics of astronomy would at least be helped with these basic. What I'll do is I'll share this Jupyter notebook file. So those who are joined later will get all the code as well, and I'll share this PPT as well. So it's basically a guide of although the points and concepts are not explained in the slides, but you can Google and read them up. So these are some of the basic concepts I covered. I think starting from ephemeris, just a very quick recap. Then I explained altitude and azimuth. Then equatorial coordinate system, what is RA and DEC. Then I took the example of liquid mirror telescope to explain zenith and use that as an example. Meridian crossing, different seasons, and almanac, how to use almanac. Solar noon, sunrise, sunset, different types of sunrise and sunset. So astronomical, nautical, civil, all that. And final example was the percentage illumination or the tithi of the moon. And there were other examples. You can look into the Skyfield website. So I think the final examples were Comet, ZTF. So I'll include this modified code as well. So you don't. So here the constellation lines are removed, but at least now you get an idea of how the this is an image from the internet. This is the path of the comet. Similar path was generated using the code. So this is also something you can do. Then there are other examples of plotting satellite paths and all. So I did not go into that, but yeah, this again, the code is a bit more involved. So if you are interested, you can jump into that as well. So yeah, I'll share these things. So the most important is this website, roadsmill.org Skyfield. So all the examples are from there. You can, if you have that, then you don't even need this notebook. Still, I'll share the notebook and the slides with you all. Okay, thank you.
Yeah.
Yeah. Okay.
Hello. Yes, about that. First of all, I would like to conclude by saying that this was one of the most interesting sessions that I've ever been to. So thank you, sir. Yes, I think everyone will agree with me. Yeah, it was one of the most.
Undoubtedly.
Yes. So I hope it was beneficial to all the participants as well. And if anyone wants to share anything about this event today or any feedback, please go ahead. And please turn on your mic and video, everyone.
At, at the outset, let me thank you, Anamika, for wonderfully coordinating.
Thank
And uh, today's day belongs to Alok. Uh, I have been interacting with him earlier too on few occasions, but this is the stuff actually I was looking for. And as if he read my mind, he planned this program. So it was so nice. And incidentally, I'm also working on the planetary positions. The reason being, I'm also a publisher of a Panchan from Hyderabad by name Varamira, which is based upon generally people do it copied from some software or some ephemeris. I have used spherical trigonometry to generate the code and I have executed and which is matching close to NASA's value. And there are certain subtle points in these calculations which require further research. And I look forward, I consider myself a novice. I look forward from help from you people. And the University of Calcutta, I should thank for organizing such a program and kindly do include me also in any your outreach programs. Don't think I'm older. I'm young enough to come and visit. So I see a lot many young people around, and I see a great future for astronomy here. And I rest today's comments with passing again special comments to Alok Mandavgane. Thank you. Wait for the group
Thank you very
photograph.
much.
We will be taking a group photo, so everyone, can you please turn on your video? You don't have to be shy.
Many are light years away.
Yes, they are.
I think only four have turned on, so you can take a screenshot of that only.
Okay, we'll take a screenshot of that then. Oh no, some people are turning on the cameras now.
Thank you.
Ready? Uh, yes, yes, exactly.
Yeah, so the second part would involve one specialized topic. So, yeah, I have covered a broad variety of general astronomy terms. So maybe we can take up one topic in particular and move ahead on that. So again, as we were discussing, research point of view, you can do calendar calculations and all. Then there is useful things if some of you are taking projects in uh, like if you want to chart something specific in the sky and if you have to learn that, then that can be one topic. So yeah, the problem is now have to be more specific. Now, this was a general talk. The next talk we'll have to define a more specific topic, and we can cover that. Yeah. Yeah, the problem is all our telescopes are in Bhopal. In fact, tomorrow is a busy day. Tomorrow is the start of IISF, India International Science Festival in NIT Bhopal. So for 4 days we'll be busy there. So MP we have no restriction. In fact, we have been to IIT BHU, we have been to BITS Pilani, different colleges. The biggest problem is transportation. So it's very difficult to take our telescopes. Still, we manage at least couple of telescopes we have been able to transport to different cities. For Pilani, I remember we went via train to Delhi, then booked a cab, and so it was very hectic. So Kolkata might be even trickier to carry.
Which telescope you use, Alok?
We have more than 20 telescopes. So I'm a part of Aryabhat Foundation. So we are based in Madhya Pradesh. So we organize numerous sky watching camps and telescope camps. So uh, we have different telescopes like small refractor ones and big. The biggest one is 12
Yeah.
inch diameter. And we have also have equatorial. So if some of you have seen my astrophotography, so those where there is we have a planetary cam and DSLR and all. So to some extent, planetary we do on a equatorial mount. So that setup we also have. So total telescopes are more than 25, in fact. So there are, and in fact, we are scattered and volunteers are scattered all over MP. Neemuch, Mandsaur, Gwalior, Indore, Ujjain. So different. In fact, one of our students, Pranshu, he's in Mumbai. He has also joined. He's studying MSc in astronomy, astrophysics. So that way, we do take telescopes away. But yeah, if you want to organize it, it might be tricky bringing on our telescope. Better to search for a telescope. Any enthusiast? I think there are a few serious amateur astronomers in Kolkata. If they have telescopes ready, will be happy to come there and organize. Otherwise, I would encourage you can also take up your on your own. So for any specialized need, we are you are welcome to invite us. But yeah, better to have a local resource in terms of telescope as well as a resource person. I think there are a few. I'm not sure of practical sky watching, but the one person I was talking about, Devi Prasad Diwari, I think he's from planetarium. I'm not sure. So he is on my Facebook. Similarly, there are other senior resource persons that you can contact. Otherwise, yeah, if you can arrange for a telescope, then we'll be happy to come and take up a session, practical session.
Does anyone else have anything to share or talk about? No.
I think I'd like to just thank Mr. Alok, like, for a novice who is not from the astronomy background. It was a very insightful session, and I honestly gained a lot of knowledge and garnered some interest in this thing. And I'd also like to thank Arjun for asking to join this and inviting me on this. So thanks a lot.
Thank you. So one more thing, I think Amritanshu has more contacts there. So he has suggested one name. Maybe you can speak up. Maybe you would know their activities more. Also, there is planetarium. So better talk to planetarium. They would know other associations as well. At least if they are open, depends on personality. So if they are open for outreach, they will connect you to the right person. If they are not proactive, then
We have to become active.
yeah.
That's a good progress. It's a good progress.
Okay, nice.
Yeah. Thank you, everyone. So
Yes,
nice
thank
of
you
you.
everyone and participants. And we will be keep coming up with more events like this. And yeah, so make sure to stay in touch with us via our social media pages and the YouTube channel that we have.
You
Okay.
have our mails. Please do communicate. We will make every effort to attend. Today, actually, I have one class at the same time. I skipped that class. That was class by Professor Amitabh Ghosh from IIT Kharagpur. He is teaching on archaeoastronomy. So today exactly the same. So I skipped that class to attend this because positional astronomy is of more interest to me than archaeoastronomy.
Yes, I hope
Thank
all
you.
of us stay in contact with each other. Have a good evening and good night.
Thank you. Good
Bye
night.
bye.
Bye bye.